Hello students, good morning to all. In this lecture, we are going to see the next topic, which is sampling for attributes. So attribute means an attribute is a qualitative characteristic which cannot be measured in terms of numbers. For example, honesty or beauty. We cannot measure beauty in numbers. Or we can say blood group or skin color or sex, male or female. So these all are attributes. So attribute cannot measure in terms of numbers, but variables we can measure in terms of numbers. So when attributes are given, how to take sample? So notation, capital N means population size, small n means sample size. We are going to use capital A notation for number of units in a population having required attribute. So how many number of units in a population having required attribute, or we can say this as a population total. Small a means number of units in a sample having required attribute. Suppose we take some sample from a population, and in that how many units are there having required attributes. So we can say this as a sample total. Now population proportion. Population proportion means proportion of required attributes in a population. Now this can be obtained by number of units in a population having required attribute divided by total number of units. So this is capital A by capital N. Q is just 1 minus P. Now small p, just like capital P, small p notation will be used for sample proportion. So sample proportion similarly is obtained by small a by small n. Q is just your 1 minus p. Capital Yi. Capital Yi notation will be capital Y taking value 1 if ith population unit has required attributes, and taking value 0 if ith population unit has not having a required attribute. Small yi notation will be small yi takes value 1 if ith sample unit has required attribute and 0 otherwise. If you can see, if you take summation I is equal to 1 to n capital Y, because Y taking value 1 when ith population unit having a required attribute, and taking value 0 if ith population unit are not having a required attribute. And capital A means number of units having required attribute in a population. So if we take summation of yi or summation yi square, because y taking value only 1 and 0, so summation yi is same as summation yi square. This will be your capital A. Similarly, if you take summation I running from 1 to small n, small yi also taking value 1 and 0. So summation of small yi is same as summation of small yi square. And this will be your A, small a. Look at this example. A population has had 10 students and the corresponding sample has 4 students. Means capital N in this case is 10. Capital N is 10. Small n is 4. Alright. The data are as follows. So these are population. So these are 10 students. In this first our required attribute is honesty, and first student is honest, second student is honest, H represents honest and NH represents not honest. So first, second, third student is honest, fourth one is not honest, fifth one is again honest. So like this data is given. So this is your population. And from this population, we take sample of size 4. And in this sample, first student came honest, second student came honest, third one is not honest, and fourth one is honest. So to understand the notations from this from this example, here capital N is 10, small n is 4. Capital A means number of units in a population having required attribute. Here required attribute is honesty. So how many students in a population having required attribute, or how many students are honest? 1, 2, 3, 4, 5, 6, 7. So A will be 7. What is meant by small a? Small a means number of units in a sample having required attribute. So in sample there are 3 honest students. So A is 3. Capital P. Capital P means population proportion. How to find population proportion? Population proportion is obtained by A by N. So this means actually, so population proportion of honest students. So capital A is 7 and capital N is 10. So this is 0.7. So in population there are 70% honest students, we can say. So Q is equal to 1 minus capital P. So this is 1 minus 0.7 and this one is 0.3. So we can say there are 30% not honest students in a population. If you write the values of yi taking value 1, if the ith population unit having required attribute. So this is honest. This student is honest. So this value is 1, this value is 1, this value is 1. This student is not honest. This y value will be 0. This one is 1, 0, 0, 1, 1, 1. Look at here. If we add this one, so 1 plus 1 plus plus up to 1, then this will be 7. This is same as capital A. So we can say now summation I is equal to 1 to capital N, capital Yi will be A if yi taking value 1 and 0. Similarly, if we take square of every value and then addition, then this is also same as your A, because 1 square is 1 and 0 square is 0. Right? Now small yi is for sample. If ith sample taking required attributes, so this will be 1, this will be 1, this is not a required attribute, so 0 and 1. If we add this 1 plus 1 plus 0 plus 1, then this will be 3, so this is same as A. So we can say summation I running from 1 to small n, small yi is your small a. And if you take square also, then also this is A. So summation I is equal to 1 to small n, small I y square is also A. Now look at this theorem. Under SRSWR or SRSWOR, obtain unbiased estimator of population proportion. Means we want to find the unbiased estimator for population proportion. Population proportion is capital P. And population total. Population total is actually your capital A. So we want to find unbiased estimator for P and A. Or this theorem may be asked like this also. Under SRSWR, prove that sample proportion is an unbiased estimator of population proportion. Means actually here we want to prove expected value of small p is equal to capital P. Means sample proportion is unbiased estimator of population proportion. And n into p, this is small p. N into p is unbiased estimator of population total. So expected value of n into small p is equal to capital A. So we want to prove this one. So proof of this theorem. Proof. Consider expected value of sample proportion. First one, expected value of sample proportion means expected value of small p. This is equal to, now small p is actually small a by n. So small a by small n, and small a, if we define small yi as 1, if ith sample unit having a required attribute, and 0 otherwise, then your a is summation y. Just now we seen summation yi upon small n. So this is equal to, now summation yi upon small n is actually your small y bar, and under SRSWR or SRSWOR, sample mean is an unbiased estimator of, you know this one, sample mean is an unbiased estimator of population mean. So this will be now, this will be capital Y bar. So capital Y bar formula is 1 upon capital N summation I running from 1 to capital N capital Y. Here capital Y is 1. It is binary variable. So this taking value 1 if ith population unit having a required attribute and 0 otherwise. So if yi is like this, then this summation y is actually your capital A. So this is capital A by capital N, and capital A by capital N is actually capital P. So we had started from expected value of small p or expected value of sample proportion, and this is capital P. So therefore expected value of small p is capital P. This means sample proportion is an unbiased estimator of population proportion in SRSWR and also in SRSWOR. To prove second one is prove that NP is an unbiased estimator of population total. So population total is capital A. So second, consider expected value of n into small p. N is constant, so we can write n into expected value of small p. And just now we proved expected value of small p is capital P. So this is n into capital P. You know capital P is actually A by n. So n gets cancelled, this will be capital A. So expected value of n into small p is capital A. This means therefore n into p is an unbiased estimator of population total. Population total is actually capital A. Now look at this remark. Estimator of P. Usually P is unknown, means population proportion is unknown. So estimator of this P is denoted by P cap, and we will going to take its estimator is sample proportion. Just like that, estimator of A is denoted by A cap and its estimator is n into small p. Now move to next theorem. Next theorem is under SRSWR obtain an expression for variance of sample proportion. Means in WR we want to find variance of sample proportion. Now sample proportion is unbiased estimator of population proportion. So this theorem may be asked like this also. Under SRSWR, obtain an expression for variance of unbiased estimator of population proportion. So this P is unbiased estimator of population proportion, means variance of unbiased estimator of population proportion is actually sample proportion. Sample proportion is small p. Or this theorem may be asked like this also. Under SRSWR, prove that variance of P is equal to PQ by N. So capital P means population proportion, Q is 1 minus 1. So proof of this theorem. Consider variance of small p under WR. Now variance of small p is A by N. So this is variance of A by N. A is summation I running from 1 to small n, small yi upon small n, where small yi is 1 if ith sample unit having a required attribute. Unit having required attribute and 0 otherwise. So if yi is like this, then summation yi is your small a. So this is your variance of small y bar. And variance of small y bar in WR already we obtained. So this is sigma square by small n. Denote this by equation number 1. Find out sigma square and put here. So consider sigma square. So sigma square, formula for sigma square population variance is 1 upon n summation I running from 1 to capital N capital Y square minus capital Y bar square. Here yi is taking only binary values. Yi is 1 if ith population unit having a required attribute, and 0 otherwise. So this is equal to summation yi square. You know summation yi square is same as summation yi. So this is a by n minus y bar is actually summation I running from 1 to capital N capital Y upon capital N whole bracket square. So y is like this, then summation yi is same as summation yi square, and which is capital A. So this will be capital A by n minus this is again capital A by n whole bracket square. So capital A by n is actually capital P minus this is P square, and P minus P square is, take P common, so this will be 1 minus P and this is P cube. So sigma square is P cube, put in equation number 1, then we get variance of P as P cube by N. So equation number 1 implies variance of small p is equal to P cube by small n. So variance of small p under WR is capital PQ upon small n. Remark, under SRSWR variance of A, already we find variance of P is PQ by N. Variance of A is actually variance of n into P. N is constant, so this will be n square into variance of P, and n square into variance of P. Variance of P is PQ by n. So variance of A under WR is n square into PQ by small n. Standard error of any estimator is just a square root of that square root of variance of that estimator. So standard error of P is root of variance of P. So standard error of P will be root of PQ by n. Usually PQ, capital P or capital Q is unknown. So we have to put their estimators, means P cap and Q cap. So P cap is P and Q cap is Q. So estimate of standard error of P is root of, take its estimators, so which is root of PQ by small n. Standard error of A means root of variance of A, and take root of this one, so this will be n into root of PQ by small n. This PQ is unknown, so put their estimators. So estimate of standard error of A is equal to n into their estimators are P and Q, small p and Q. So this will be capital N into root of small pq by n. Thank you.